Hello, good afternoon, everybody, and welcome to today's designTimber webinar. In a minute, we'll be hearing from the team behind the fascinating field station project. But while we're waiting for everyone to join, I'm just going to say a few words about Timber Development UK. My name's Matt Milton. I'm Editorial and Publications Manager here. And TD UK is the biggest timber supply chain organisation in the UK. If you work with wood, this is where you belong. We formed when TRADA and the Timber Trade Federation merged. That was in 2021. So if you were a TRADA member, you're now a TD UK member. We represent everyone from supplier to specifier, including architects, engineers, contractors, craftspeople, and everybody in between. Here you can see our three key missions: connect the supply chain, lead best practice, and accelerate a low carbon future. And we carry out our aims via events such as this one, and via our ever expanding resources library, and also the influential work we do with politicians and policymakers to keep timber to the fore. Here you can see a few examples of some of our publications. There's designTimber, that's our quarterly print magazine, which is packed full of interesting news and stories and CPD about timber buildings, timber designs. And there you can see one of our many case studies. That's Durley-Chine Environmental Hub, which was also one of the webinars in this series. So if you want to know more about that, you can download the case study if you're a member, or you can head over to our YouTube channel and watch the really good webinar on that. You can also see an example there, 2024 embodied carbon data for timber products. That's one of our timber knowledge sheets. We have a knowledge library packed with many more of those. They cover all the essential timber topics, from building regulations, fire safety, design advice, and much, much, much more. You can also see there one of our publications, Timber Policy. We know that timber is a big part of decarbonising construction, and we're working very hard to ensure the next government takes that on board. That is a particularly interesting document because it looks at what other countries are doing to accelerate timber, both nationally and regionally. You can download that from our site. We urge you all to join us. I'm sure many of you are already members. We have a lot of free resources that anybody can access, but we also have lots of member-only exclusives. Some of the knowledge sheets that I was just showing you are part of that. Plus, we've recently launched Find Your Timber Partner, which is a kind of shop window for our members. It allows all our members to advertise all the great work they're doing to potential clients, show off their projects, show off their products. Lastly, I want to tell you all about our exciting new conference. This is coming up in a couple of weeks' time on 26th of June. It's going to be a truly inspiring day, I think. We've got an exceptionally good lineup of presentations, panels, networking opportunities, discussions. We're bringing together clients, architects, engineers, developers, insurers and manufacturers and others. It's also an absolute bargain, I think. It's just £30 for members and £100 for non-members. That price includes lunch and post-conference networking drinks, and of course all the brilliant content and CPDs during the day. You can hear all about things like the Phoenix development, which is the UK's largest timber development ever, over in Lewes, plus among other things, a closing session hearing from architects Declare, ACAN, and others about what we want from the next government. I do urge you to go over to our website, see what else is happening that day, because I think it will be a truly exceptional event. Do watch out for other webinars we've got coming up in this series. We've got the Boat House. I'll show you more about that later. Eton Sports and Aquatics Centre and the NMS building. Some great projects. So yes, I'm going to hand over now to Emmanuel and Kate. Just a bit of housekeeping. If you have any questions, do take a look at the Q&A box. If you kind of scroll your cursor to the bottom of the screen, you should find that Q&A box. And do type in questions and we'll keep an eye out for them, because there'll be an opportunity to answer them at the end. So yeah, Just going to stop sharing my screen and hand over to Kate and Emmanuel. I think you might be muted.
Sorry, unmuting. Hello, everyone. First of all, thank you for inviting us to speak. It's a real pleasure to talk as part of this series. I'm Kate Davies. This is Emmanuel Vercruysse. We run the Hook Park campus, which is the satellite campus for the Architectural Association based down in Dorset in the UK. The Architectural Association is based in London. And we run the postgraduate design and make program, which is a residential postgraduate architecture course that is based down in Hook, down in our woodland campus. It's a pretty amazing thing. I think pretty unique thing for an architecture school to own a woodland. So the Architectural Association owns this woodland you can see on the screen. It's 150 hectares of working woodland. So we have a forest management plan. We manage the forest, and the program builds one-to-one architectural prototypes and buildings from timber, from the timber supplied by our own forest. We have roughly 17 different species. This is a kind of diagram of the different plots of our working woodland. And the kind of immediate context surrounding the campus and its academic program is really an amazing opportunity to think about a connection between the design of timber architecture and the education of architects in timber architecture in direct relationship to the forest where that material is grown. So one of the things we're interested in is a kind of engagement with some of the natural geometries of timber as it's grown. Also some engagement with perhaps the smaller diameter timbers that are actually a byproduct of the forestry process, which is in a way maybe a slight counterpoint to the standardized uniform timber that we might see in a timber yard. Our direct engagement with the forest, with the students, and it means that we can, the forest becomes a part of the education here. We have our own forester, who's this chap, Chris Sad, who works very closely with the students. They get to be involved in the whole timber supply chain, from discussions about forest management, planting, all the way through to being involved with the felling of the trees that they use in their design projects. We also have a sawmill on site where we mill the timber that we produce for the projects. And as I say, there's a kind of, where we find it really interesting as an educational model is that the scope of the design thinking, the scope of the brief for the project stretches back beyond your normal kind of engagement with a timber yard, all the way back to the planning and management of the forest, and the students are wholly involved in the whole of that conversation. So I'll pass on to Emmanuel, who might give a bit more context about the program in general, and then we're going to hand over to Romain and Garrett to explain in more detail the field station project.
Right, thanks, Kate. So if you look a little bit closer at the type of research that happens at Hook Park, there's generally two strands. We're really interested in natural geometry, so timber in the round. So that's one of the components. In this case, here's Ankai, one of the previous students who's really interested into steam bending an entire tree. So we're really interested in all these logistics that are involved in manipulating the timber and constructing it. So fundamentally, we look at timber production, and if we look at the standing tree, we think 50% of a tree can make it as a building component that seem to be efficient from a timber production point of view. There's lots of components that are not of interest. So the image that we're looking at is an assembly of natural forking beech trees that we turn into Virendale truss. So forking geometry is problematic from a timber production point of view, from an industrial harvesting. But we all know historically this is one of the strongest parts of a tree. So we are interested in looking at efficiency of timber production, but also working with these materials that are sidelined. So this is looking at up into the finished building. And the other research that's happened is looking at engineered timber. So here we are looking at a glue laminated structural frame. So we do these large scale production. Everything is done in-house, so the glue lamination and the production and the assembly. And then this is the composed frame. So we are interested in these tacit experiences, getting hands-on material, building large scale, but we're also interested in locating advanced technologies. So we're using a robotic system and we integrate tools that are commonplace within timber industry. So chainsaws and bandsaws are all fair game to be seen as end effectors to attach onto the robot. And this leads to quite surprising kind of encounters. So this is natural, this is a structural component and it's natural geometry. So we operate really precisely on these pieces. And then this is the conjunction between these really precise connection points and the natural geometries. Because we do everything in-house, we have these beautiful moments where architecture is 75% complete and allows to these magic moments where we can kind of stop and take a snapshot and understand all the processes. So these are some of the research projects that happen at Hook Park, and the field station is one of them. So I'm just going to pass very briefly back to Kate to just locate the field station, and then we're going to pass on to Garrett and Romain, who were two students that are part of an 11-strong unit of students that built the field station.
Yeah, so each brief for the students starts with a kind of provocation and a framing of a programmatic brief from which the students develop their work collectively. The field station was imagined as a kind of enclosed multi-use structure that would be somewhat remote from the main campus, which you saw in that aerial photograph, out in the forest at Hook. The brief for it was to provide a shelter for groups who want to teach out in the forest, but also a shelter for our forester, also for passing walkers and horse riders. We have a lot of visitors it's an open access forest, so we have the public walking through our forest. A place for forest research to happen out in the forest. It's also probably one of the only places on site where we have a view to our neighboring kind of environment, to a kind of our neighboring landholders. And what's interesting about that is we wanted the field station to be both a kind of structure and a shelter, but also some kind of observatory for long-term change. So both observing the changes in planting in the immediate surroundings to the location that we identified, but also looking to the neighboring estate who are undergoing a big rewilding project at the moment to be kind of conceptually a project which is about looking at long-term strategies for the landscape. So that was the brief and the provocation that we set our students. It was an amazing cohort. Romain and Garrett are two of, as Emmanuel said, a bigger group of students that work collectively on this project. And I'm going to hand over to them to explain the project through in more detail.
Thanks, Kate and Emmanuel. Let me share my screen. Okay, you guys seeing that?
Yes,
Amazing.
great, thanks.
Yes, as Kate and Emmanuel said, me and Romain were two of the students who are part of a larger group effort. A much larger group effort all the way from the tree to the final build. There was 10 of us in the cohort, and then of course there's the larger group at Hook Park, and then we were working in tandem with the Arup team, come up with the structural design for the building. As Kate was explaining, this exists within the context of Hook Park. And Hook Park is really the feedstock for all of our buildings. And there's a variety of different forestry regimes that exist here, from softwoods, short rotation, to hardwood and long rotation. And it really becomes a matter of what sort of wood is being harvested at that time that we can then use in our final builds. Hook also brings a pretty interesting dynamic when you start looking at England as a whole. It's roughly larger than 98% of the woodlands in England per the National Forest Inventory that was conducted in 2020. But it is also, 86% of the woodland in England consists of forests smaller than Hook Park. So it sort of exists at this industrial scale, but because of the intimate nature of how we engage with the forest, it kind of sheds light on how you might be able to manage a smaller set of woodlands sort of existing in this happy middle space. This is a mapping of Hook Park in the thinning schedule for when we were there in 2022. You can see in red are all the areas that were going to be thinned, and it was roughly 0.25% of those trees were going to be cut down. A lot of them were going to be beech, and the beech at Hook had been overgrown and been planted in the 50s or 60s, and so that was really going to be the primary feedstock for the building that we're going to work with, or the construction material that we wanted to work with. And so when they thin this material, a harvester, this industrial machine, comes out and it cuts down 25% of the trees, takes the primary logs off to be milled elsewhere off site, and typically leaves behind what we consider this forest residue. And this is crown timber, branch timber, anywhere between 50 mil to 100 mil. That is still of good structural grade, but is discarded and left into the forest. Maybe typically previous in another life, it would have been used as firewood, but in today's kind of marketplace, it just doesn't have much value. And so we were really tasked with what could we do with this material, roughly 1 meter in length? How can we use it in some sort of architectural application? And it was decided and prompted to us by our directors to explore using it in a space truss or a space frame sort of typology. And something that I think is important to look at Hook is there's this legacy of trying to use the full tree in the round to make most efficient use of that wood. And so there's examples of using the trunk timber, which typically makes up 60% of the biomass, the primary forks, which Emmanuel talked about using in a Varendale trust. And what we were looking at were really the crown timber, the crown branches, which can make anywhere of 25% of that above ground biomass. What's interesting, though, is there was a study done by UCL that did terrestrial laser scans of broadleaf trees throughout the UK. And typically what you find is as trees get older, the ways of measuring that volume, they're kind of inefficient to take into account all the kind of growth and natural geometries that exist in that tree. And they were finding that older trees were actually 1.7 times greater in volume than what they had accounted for in their models. And in a place like Hook, where a lot of the beech is 60 years old and is out of rotation and has grown quite large, you can assume that there's even more volume that exists in these areas that are typically not used in the current industrial methods or industrial standards. And so it becomes important to take use of the crown timber and these other unusable building stocks in our in construction as we start to make use of more of these broadleaf trees in the UK that may be that are out of rotation and have grown over what they would typically in a shorter forestry rotation. So this gives you a glimpse into kind of what it looks like for students to go out into the forest and to source some of this round wood that has been left discarded on the ground. Typically, it meant that we would go out with a handsaw, a gauge to make sure it was of the right diameter, and some sort of piece of wood to give us a general dimension that we're able to find the right length that we needed. And then all of that material is going to be then used to create a space frame, space truss, the field station. Just before we dig into the details of the construction, as Kate mentioned, it's a program that kind of invites people to come into the forest to view the changing surroundings, then to host a variety of events or just to relax and engage in the natural setting. Here are two images of a recent yoga class that was hosted there, and then an end of year party that was hosted by the AA at the field station. And so I'm going to pass it off to Romain to speak to the finer details of it.
Yes, so the space stress, we're going to dive into it a bit more now. So the structural grid is of around 75 by 75 centimeters, covering 14 by 10 days, spanning around 11 by 8 meters, and a total surface of approximately 90 square meters. So there are actually 3 points of contact with 6 tree forks harvested from the forest. So there are actually primary and secondary tree forks. So the primary are coming in direct contact with the space truss, and the secondary ones are acting as additional supports to the primary ones. So you could see actually at the bottom here, the tree forks are braced together with a beam, and they act as the primary structure to the platform also. So here you can also see a bit of a breakdown of the space truss, and it contains 80 by 30 engineered ash cords. So you can see 2 at the top and 2 at the bottom. So they notch into one another by 20 millimeters. And these cords are sandwiched with robotically milled roundwood braces of varying diameters between around 50, 70, and 90 millimeters. So these braces operate under compression through the pre-stressed 10 millimeter threaded rods that are also clamped by 75 by 75 millimeter galv washers. So the areas actually with heavier load require welded steel plate. You can see here, so that they could welcome the roundwood brace meeting the tree fork. So areas, yes, with the higher load ask for a 90 millimeter roundwood brace pinned to the welded steel plates that are sandwiched between the cords. And radially, the further they get from the tree forks, they decrease in diameter. So from firstly 90 millimeters to around 70 millimeters to then 50 millimeters. Yeah, so you can see that actually with the 3.6, this is the point where the tree fork meets the truss, and then from there the diameters get smaller. Yeah. So there were a series of prototypes that were developed between January and June of 2022. And firstly, we wanted to understand first how to work with roundwood by hand, and then further on develop it through workshop machinery such as the bandsaw and the table saw. And finally, with robotic configurations to ensure that there would be precision throughout the 256 roundwood braces that were being milled. So the first jig was made, this was the first jig exploring the space truss configuration. So ensuring that the roundwood brace could sit in between the cords with its routed shoulders. So this is a jig that Jin actually worked on early on, and the classmate Jin that worked on it early on. And to finally our final configuration, which saw a feeding station for the KUKA robot to perform a scan via the 3D camera before operating a series of cuts through the circular saw fixed on the lathe, you can see on the left, all within a time frame of approximately 7 minutes. So we'll show you a couple of videos now. So here you can see the feeding station actually manually fed and scanning through a series of pictures with this 3D camera. So a script was made by Wyatt, our robotic developer, and this you can see here is processing onto Rhino and Grasshopper to identify the center lines and locate the notches that are to be cut by the circular saw in the chamber. Yes, and finally, when it's been processed on the computer, it is then sent to the robot and cut on the circular saw to make 15 cuts. So you can notice in this picture actually two different types of notches. And I'll explain this in the next slide. Yeah, so there are 5 cuts for the flat face you can see at the bottom, and 10 cuts that were for the routed face to welcome the threaded rod. And this would ensure that the loads would transfer to the center of the cords evenly. So yes, a total of 256 roundwood braces. And then now in this next part, diving deeper into the components, we could kind of like to consider them as locators because they played a crucial role in the streamlining of the off-grid assembly process on site. So this, for example, is the keystone operating as the vertical locators, ensuring the proper location of the threaded rods and the spacing of the cord between one another, and the stoppers for the roundwood braces during assembly. The node connectors, as you saw previously, they provide added strength in areas of higher load, so closer to the tree fork supports. So there are 2 types of nodes depending on the cord assembly, and a total of 168 pieces of 5mm steel welded to make 12 nodes, then galved for protection. The splice joints were needed to increase the cord lengths due to a maximum sawmill length of 5.5 meters. And so this was assembled on site, and the cords were butt jointed together, bolted and supported by the U-galv steel plates. And here you see the top connectors for the tree forks. So this welcomes a 40mm steel bar slotted into the tree fork to bolt the space trusses threaded rod into place. And we also made a template that was to ensure the correct positioning of the tree forks, to ensure that what had been drawn digitally was actually what was placed physically. And the tree fork, the bottom connectors, it's held above ground for water protection. And it was connected in the workshop, but then just placed on this screw pile, which goes 6 meters deep into the ground. And we did this in a way so that we could offer rotational flexibility while we were placing the tree forks on site. So yeah, this is a kind of like an overview actually of the whole space truss. You can see all the components, so it's easily flat packable to transport on site for a much smoother off-grid assembly using strictly only battery-powered hand tools. And Garrett will actually be able to dive into this a little bit deeper now in the next slides.
Yes, so our construction site was roughly a mile from the workshop and the Greater Hook Park campus. You can see on the right, it existed at the edge of the public footpath, and it really made for a beautiful and lovely experience in the late summer, early fall, but of course gets very wet as you transition to late fall and winter. One difficulty of working out in these conditions was trying to build a flat and straight space frame on what was a sloping site. And you can see in the GIF on the left that we were able to utilize an existing mass timber, basically frame from a domino, a Maison domino project that we had some leftover mass timber beams from, to create a flat platform, a true platform that we could then build off of. These images are roughly, I would say, a few days apart. The total construction of the space frame on site took about 2 weeks. So you can see in the top left, this is with the platform below, and you can see we kind of have to piecemeal the structure together being all these loose fit pieces, it really does want to just unfold on itself and collapse and can create a lot of difficulties in the field. But the moment you start to tension those rods and you start to get the connections together, it kind of fits together quite seamlessly, and you start hitting your groove, and then it all goes together quite nicely. This is a short animation kind of showing the choreography of the job site. At any time there was 6 or 7 of us out there, and it was sort of necessary in order to get the cords up and the timber in place, and then to be able to tension it. So it kind of becomes, once you get into the groove of it, a sort of a dance out in the forest, creating the space frame. The final and kind of penultimate experience of the construction on site was to bring a crane out into the forest to lift up this 3-ton space frame and to place it on top of the tree forks. This was quite a fun learning experience for the students, trying to convince some of the crane operators in nearby Dorset to come out and to do this work. I think a few of them were a little bit not sure if this would be doable, but we found one who was willing to do so, and yeah, everything went according to plan. And this is an image from below where you can see we had to drop sort of the 3 primary tension rods directly over the tree forks, where then you would go in, you can see it with this gentleman right here, and sort of tighten them against the tree fork columns. So in total, these images were taken roughly 6 months apart. This is the site before we'd selected it and done any of the removal of vegetation. And then this is the completed site in the middle of winter. And some final photos of what that looks like right now. It's totally open to the public, so I definitely recommend anybody in the area to go check it out. But it definitely creates this sort of lovely dappling of light that comes across the branches and the space frame. And yeah, it was a fantastic experience. Pass it back to Romain.
Yeah, so yeah, we got to do some post documentation, and it gave us the opportunity to overlay the LiDAR scan with the built field station, right? So or what was drawn. So we noticed that there was a slight rotation with one of the tree forks, which resulted with a 1 degree offset vertically and a 3 degree offset horizontally. Yeah. So yeah, living, studying, and working in the forest, and like witnessing all of the stages of transformation of the timber really gave us a kind of kinship to not only the field station but to Hook Park. So working with green timber means that for the next three years we must also like tighten the loose connections as the wood shrinks. So Garrett and I came back to Hook last year during the summer, and we got to perform somewhat a kind of a ritual, I guess, for us for the next couple of years. My secondary thesis saw looking at how to extend the lifetime of the field station through perpetual maintenance and intensive care. And so this iteration was looking specifically at the brace, and if there were to be a brace to be broken, a part of its length could be replaced by a rig to then deploy it back into the space truss. And this was kind of like an open-ended conversation where kind of any type of student coming into Hook could also engage with the field station in their own way and apply their own kind of option to rigging or deploying the broken branch. And in terms of what we've been doing since Hook, so with Maisie and James, who were part of the cohort after us, we've been collaborating with a festival in Belgium, where we got to also use their stock material, but at the same time, we got to coppice also some hazel from Hook and use it as part of this furniture series that we made for them, and turn them into the wedges for these benches and tables and part of a pair of chairs. And this year continues on, so with a similar approach, but this time using both harvested roundwood from Hook and Horse Festival, so the Asiat Park, to build a playful drinking water fountain with a low resolution roundwood truss to welcome the participation of volunteers. So we also documented the stages of transformation in an attempt to make this knowledge as accessible to the wider audience as possible. And so now I'll pass it on to Adam to dive in deeper on the structural aspects of the field station.
Thanks
I'm just gonna,
very much. Oh yeah, go ahead.
I was just going to remind everybody to do ask any questions. Use that Q&A box. Thank you. Sorry, Adam, carry on.
Perfect. Thanks very much, Romain and Garrett. That was amazing. So you guys have covered it really well, how this structure fits together. I'm going to go in a little bit more detail about the kind of principles behind this, and how we came up with this final design. So apologies from our structural director, Francis Archer. He's been heavily involved in lots of the AA projects over the years, and always throws in a lot of his ideas into the principles behind these projects. So as Garrett and Romain have so clearly explained, one of the main drivers behind this project architecturally was to use the kind of small diameter crown timber, and early on there was an idea of a space frame or a truss system. So yeah, you've seen what kind of small diameter, 50 to 90 mil we're talking about. So immediately our structural reaction to that was such small diameter members, we're going to really struggle to get a tension connection at the ends of those, as something we wanted to avoid. And in general, the idea was to minimize the amount of steel at the connections of those roundwood members. And for constructability and complexity, we also wanted to avoid too many of these members meeting at any one node. So those were kind of our initial structural reaction. So I've just found this image off Google. Apologies if it's your project. I'm sure there's a very good reason why it needed all these connectors, but this is the kind of thing we thought wouldn't be practical for the kind of small diameter roundwoods that we were looking to use. So our solution was to ensure that these roundwood members are always in compression, and then we could just design simple bearing connections at the end and didn't need to get tension into those. And how we achieved that was by using these 8 mil threaded rods vertical at every node, which we tighten up and pre-stress. So you almost clamp these kind of layers of branches together and put everything in pre-compression. And that basically simplifies all the connections. And as you've seen, that's the obvious next step. So a little bit more about what this structure is. So it looks quite complicated. There's a lot of individual components, but at its core, it's kind of a series of planar trusses in 2 directions. So I've just pulled out some from the middle there. And as you can see, at any one node, you've got 2 roundwoods meeting at the top and 2 at the bottom. So there's never more than 2 roundwoods at any one node. So a little bit around the pre-stress principle. So this kind of lattice of trusses under a set of support conditions. Some of these diagonals will naturally want to go into tension and some of them in compression under gravity. And what we can do is we can add to that a pre-stress case. So we tighten up all of these rods, all the rods go into tension and all the diagonals go into compression. And then if you add those 2 load cases together, you kind of get a resultant where all the roundwoods end up staying in a bit of compression, enough that they don't go slack effectively. So that's the kind of main principle, and a little bit of kind of mathsy stuff behind the idea. So we kind of worked out that the smallest module that's in equilibrium was a little 2x2 bay. And you can see there on the left some force diagrams. So red is the maximum tension, blue is compression. And that's what the equilibrium looks like when you pre-stress up those rods. And of course, as we find with many of these projects, Francis has usually made a little model of this in his garden 30 years ago. So there's a tensegrity version along a similar principle. So if you replace all those members that are in tension with ties or strings in this case, you can get this thing to work under vertical equilibrium. Obviously, it's not very stable in that tensegrity version, as you can see. So this is kind of how we approach the pre-stressing idea. So we could build up a whole set of pre-stresses from these little modules by adding up different bits and work out the kind of idealized pre-stress case based on where the supports were. And then we could rationalize that into something that we could kind of put into the structure. So we had an idea of this pre-stress, and this was all developed, of course, in close collaboration with the students. And very early on, they built this great prototype, which was up in London, which we went down to have a look at, and that's the back of Francis's head. And this taught us a lot of things about the nodes and how this was put together. We spotted some things about things not quite noding out in some of the types of connections. And from there, that really gave us a bit of confidence that this system could work, and also gave us a good point to develop the connection further in coordination with the students. So yeah, here's a quick kind of, I think you've already been talked through it super clearly, but here's the components. So those pre-stressing rods with a steel bearing plate. Sometimes it's an angle to hold things in place. And then the roundwoods with their tongues that slot in bearing connections. And yeah, so there's a nice close-up of that in reality. And you've already seen this much prettier architectural diagram with a couple of specials, which I'll talk about in a bit. Tensioning up the rods. So the workshop manager at Hook built a few different prototypes and frames to give us some ideas of how much force we were putting into these tensioned rods. And there was a couple of goes at this, different prototypes. And I think we ended up using a torque wrench to kind of get an idea of how much pre-stress we were putting into these rods. As all of you who design with timber will know, bearing perpendicular to the grain is always an issue that we have to deal with. And we had that where the diagonals come into the chords. So in many cases, the forces were of a size that we could just design for that. But where we couldn't, mainly near the supports, we had some steel rather inserts, which take all the load through the steel and into the bearing plate or support. So we don't have to rely on the cross grain bearing in those cases. Stability. So yeah, this has already been touched on, but the kind of simplified diagram for stability is 3 A-frames on plan and arranged kind of roughly around a circle. So they give a bit of torsional resistance globally. And the guys scanned in all the real life tree forks, which we could then go back and forth and arrange in 3D and try and approximate this diagram to give some stability. Other things we have to consider, uplift. So this structure is a freestanding canopy. So when the wind blows, this wants to lift up. And this is what prompted some of the pocket connections that you saw earlier. So the whole structure is tied down into the tree forks, and the tree forks at the bottom are, as you saw, flitched in. And so they can take a load reversal, a tension load down into the foundations. Which themselves are screw piles. Hook Park has some experience using these previously, and were a good fit for the kind of scale of loads that this relatively small structure was giving us. Yeah, so that's the main whiz tour of the structural ideas behind this, and some construction photos, all credit to the students at the AA, some robot photos. This was a video I got sent by them of this lifting up off the ground for the first time, which was really great to see. Supporting frames at similar points to the permanent supports, so that the load condition was similar to what it would see in the permanent case. And that's it in the air. And finally in place. So yeah, thanks very much to Emmanuel, Garrett, Romain, all the students at Hook Park. It was a really enjoyable collaboration and something kind of a bit experimental structurally that was really enjoyable to be involved in.
Well, thank you very much, everyone. That was great. We've got some time for some questions now. I've been keeping an eye on the Q&A, and there's a few things that I'll raise, but feel free to add some more, everyone. I thought I would start with, it could be that Adam's just answered this, but as I'm not an engineer, I'll bring this one up. Can you describe how the structural performance of the natural components is reliably calculated?
Yeah, so we kind of did initial calculations, assuming these are cylindrical struts effectively, and kept the stresses very low in those. So assumed a low grade of timber, keep the stresses low so that they're not kind of liable to buckling, and then confirm that with testing and prototyping on site. So that's the kind of advantage of Hook Park. You can get these things built quickly at smaller and then bigger scales, and that helps confirm the kind of initial calcs. And the kind of high level calcs also informed where we'd need to put the larger diameter elements and the smaller ones, which could then be tested.
Great, thanks. And on a sort of similar note, had a very specific question asking about the risk of an unforeseen load case causing a compression element going into tension. I don't know if you'd like to answer that.
Yeah, so it's not super immediately obvious from looking at the structure, but there is some redundancy in this structure because you've got trusses in two directions. So we did test a load case where you take the pre-stress off, and there is still a kind of ultimate load case which gets back to the supports. In theory, some of the elements would become loose, some of the diagonals, and not do anything in that case. But there is still a load path that the roof stands up without the pre-stress.
Great, thanks. We had a question about greenwood. I think Romain, you mentioned that the wood would shrink over time. I think somebody was asking about greenwood splitting as it begins to dry. So I thought I'd ask that question, but also maybe tag a couple of other questions on just about working with greenwood generally. You know, how do you find it? You know, and what sort of is it something that you'd sort of like to kind of work with more in the future in terms of sort of other uses and other projects? So sort of yeah, I mean, the greenwood question about splitting and I suppose general considerations to bear in mind, but also, yeah, how do you feel about working with greenwood?
Yeah, actually, I remember this was the conversation we were having quite a bit with Chris, and I remember when we were putting one of the tree forks, or when we had cut one of the tree forks, we had debarked it. We had let it stay for, I think it was around a month or two even. And we had just seen one of the tree forks was just, it almost looked like it was splitting in two. And we were just asking Chris if this was okay. Obviously, you know, this was the tree fork that we had to use because we had scanned it, right, and we had included it within our final design and calculation. So there was very little room for flexibility. Ultimately, like technically, I'm not entirely sure why that's fine, but Chris was telling us that there was no. So Chris, the head forester, was telling us that there was no issue with this, and he was still astonished at how big this split was.
I'll just add real quick. So yeah, with the tree forks, you would get visible splits, which then we were confirmed that they would be still fine structurally. With the small diameter round wood, it would shrink so that we had to come back and retension the space frame because you had loose braces. And then with the ash cores, which were also relatively green, and Emmanuel will be able to explain more how Hook deals with sort of green wood because you're on such a fast timeline, you don't really have time to dry these out. It became more of a matter of either having to cut new stock because the ash cord would just kink in one direction, or it would, you know, as it dries, it just irregularly kind of deforms the integrity of the cord. And so I think in some of those cases, we actually had to get rid of some of the cords that had bent too much because of all the components in the space frame. We really need those cords to be fairly true.
Mhm. Yeah, we kind of went through some sort of like visual grading, right? So we just visually graded the timber, the greenwood, the roundwood, and then from there we decided if we would keep it, if we could keep it for the space truss. But I think also just to add to the second question you were asking was, I think there's a lot of potential and interest in using the roundwood, right? The small diameter roundwood, because it's quite accessible, right? And it's essentially waste. So it's kind of free for anyone to use and play around with. And part of like the thing that we're trying to explore now, so with these collaborations with this festival, is trying to use roundwood in a kind of like a low resolution configuration or application, so that then you can promote using this material with volunteers and kind of create a community out of through architecture and construction.
If I may just add one thing about the splitting, obviously checking within green wood, the splitting is a natural phenomena. So the timber dries out and the tension needs to go somewhere. Recently, what we've employed to try and deal with this is something that's called a release cut. So we actually make an incision into the timber to encourage the checking and the splitting to happen where we want it to. So this is a practice which is commonplace, particularly in Japanese methodologies. So you encourage the timber to split in particular places by introducing a release.
Thank you. That's great. We have a question about the screw piles, asking about the length of them, whether that was due to ground conditions, or if there's anything else you'd also like to mention about the screw piles, foundations.
I'll add, you know, at Hook, we're kind of at the mercy of what is on site, what's been used previously, right? Like all these projects are a legacy of previous work. And so we just so happened to have some screw piles on site that we could reuse. And it was already known that soil in the area wasn't great. And we had just enough length of screw pile that on the very last screw pile, it wasn't hitting the torque that we needed in order to get the structural requirements. And then on that last foot, I think we had 6 meters, or last meter, it hit that amount. So we just made it where we had the exact material we needed to build those structural components. But yeah, part of it's what we have, and part of it's being light on the land. And you know, this is going to be a flat packed element. We need to be able to take down and disassemble the structure, and that really wouldn't be conducive to using anything like concrete piers or a spread footing or anything of that nature.
But this is also where our lovely collaboration with Arup comes into play. So we have a lovely relationship in kind. So they help us with the structural resolution. So Adam and Francis just gave us some newtons that we need to hit, and the screw pile, just the methodology, the head of the screw pile that gets a force feedback, which is in newton. So we just needed to get to a resistance, and if it met that resistance, then it was stable enough. So we just had to add a bit more length, as Garrett just mentioned, to get to those numbers.
Thank you. I sort of wanted to ask a kind of more general question about the kind of applicability and sort of learning that you take from a project like this, with regard to, you know, other sort of typical projects that an architect or engineer might work on. I mean, we were just talking about screw piles, and I do encounter a lot of, say, timber-based domestic extensions, for example, that might use screw piles. But I'm just wondering sort of whether there are sort of lessons learned or things you've taken from this project that you can imagine informing your practice in more kind of conventional sort of mainstream projects, for anybody that wants to answer that one.
Yeah, I think so. At least in my case, I don't have much professional experience, and I just worked a year and a half or 2 years before going into the master's. So this is kind of my basis, right? So it was the first building I got to build, right? And actually being involved in it, heavily involved in it, and witnessing all of the stages. It's now kind of, I'm looking at how this can actually be applied within the professional realm. So I think it would be interesting to now see how the whole, compare this supply chain that we've undergone within Hook Park and try to compare it within this industrial supply chain and see how how one can inform another or vice versa, right? So I think that for me is something that's interesting to explore right now.
Yeah, thanks. Yes, I
mean,
can
I'm-
imagine that. Sorry,
Sorry.
go ahead. No, please, don't want to interrupt.
No, I was just going to say something maybe broader as well, that, I mean, we are uniquely operating within an educational context. I think one of the things that really enables is, I suppose, an approach to material supply, or an approach to connection with the source of where the materials come from. So like I was saying in the introduction, I think within an educational framework, it's really important that we're introducing a conversation within the student body about the scope of design being broader than maybe it traditionally is, and that the agency of designers to be involved or to understand or to conceive of the supply chain as a part of the conversation about architecture. I think more broadly and kind of overarchingly, that's territory that we find really interesting. As a system, it's something that's part of, I suppose one thing to say is that all of the prototypes and experiments that we do are part of an ongoing developing strand of research. So we will have students currently who are building on some of the lessons that were learned from the field station, developing maybe alternative systems. So it's also part of a continuum, I suppose. It's quite an amazing system because it's as the guys were saying, it flat packs into the back of a van. And there's something amazing about that in itself, that I think is something that we've certainly been in conversations with other people about potentially deploying this in other situations for other projects. So maybe more directly applicable than some of the other projects that have happened at Hook in the past.
Yeah, thank you very much. Yeah, I mean, it certainly feels like I'm sort of seeing more and more projects that take a kind of devolved sort of attitude to what they're making, you know, finding sort of local materials, being, you know, scrupulously kind of economical with what they're using, you know, optimizing all the materials. So yes, and as you say, part of a sort of broader continuum. Well, thank you very much. I think we've sort of answered all the questions that people brought up.
I think there was, sorry to interrupt, I think there was a question about forestry, which I'm very happy to.
Yes,
genuinely.
you're right. Please go ahead. Yeah.
I mean, I would say that that's the domain of our head forester, Chris. So he has all the kind of finer details are down to him. But in general, it was a question about how we decide which species are grown next to each other. I mean, some of that is forestry is a very long experiment, a long time scale project, right? We're talking cycles of 50 years, if not more. What we have in place is what's called a woodland management plan, which is developed together with the Forestry Commission, that gives us a felling license for 10 years, and that's renewed every 10 years. So it's a slightly complex conversation, so I won't go into full details, but basically we're balancing environmental and economic, so that'll be like timber yield, public access, forest resilience, those kinds of things against each other within that management plan. And a lot of it is the forest is something that the AA obviously inherited. The majority of the forest is inherited. So in 1947, 90% of this forest was clear felled and replanted with predominantly beech and Norway spruce, with a little bit of ancient woodland fragments remaining. And really what we're working towards now, I think what's interesting as a conversation that's happening now is we're developing 100-year plan for this forest, which looks to actually actively diversify and complexify it. And that again is a very big conversation. That's another hour-long lecture. But in a nutshell, if we complexify the forest, we give it greater resilience to pests and diseases and to climate change. Changing climates are a big threat to some of the species that are in our forest at the moment. And it also helps to build biodiversity of the forest. So yeah, it's an ongoing conversation. We didn't decide, let's say, which species were planted next to each other. That in some ways was decided a very long time ago, but we do have a long-term plan for how that might develop 100 years into the future.
Great, thank you very much. I think we are going to have to wrap it up there. So yes, thanks again to our panel. And I'll just leave you quickly with a reminder of the final webinars in this year's series. Do check out the Boathouse, the next one on 3rd of July. It's a lovely project. As you can see from this slide, beautiful, elegant design, entirely wood, uses no metal fixings at all. Some images there will give you a little sneak preview of what to expect. But yes, do book your place for that one. And thanks again. Have a great afternoon. Thank you. Bye-bye.
Thank you, Judge.